For today. So we're going to start with looking at test 4, which is sections 5.1 through 5.4. The topics in this chapter, generally speaking, have to do with energy. Okay, work is a form of energy. Power is the rate at which energy is transferred or work is done. But the general topic for this chapter is energy. Energy is measured in joules, right? Energy is measured in joules. The other units that were new in this section were watts. Watts are the units for power, and we know that a watt is really a joule per second. And in case you forget what that really is, think about the formula for power. Power can be defined as work over time, and work is measured in joules, and time is measured in seconds. Therefore, this is what a watt really is, a joule per second. Why do I always indicate the units? Why is it useful to remember what the units are for certain things?
If you're given a problem with joules and seconds, you know that's work over time.
Yeah, if you're given a problem and it says, something with watts as a unit, you know it's going to be referring to power. If you see something that says joules as a unit, either it's work or kinetic energy or potential energy or some form of energy. So it's good to know what the units are for each thing. Section 5.1 was our definition of work and what work is. Can somebody remind me what the definition of work is, or the formula rather for work is?
It's like the amount of force you exert.
Good. Keep going.
Times the distance.
Good. There was one other thing.
Theta.
Good. Now, follow up for you, Victoria. Do you remember what theta was?
0 when it's moving in the horizontal direction.
Okay.
Or 1, maybe 1, right? Or I don't know.
It comes out to be 1, and theta is 0 if the force is the same direction of motion. But what is theta? Theta is the angle between what? Theta is the angle between? The what? Good. The force and the distance, or the force and the motion, whatever you'd like to call it. So, for example, if you have a force applied like so, yet the object is moving to the right like this, that's the direction of motion. If you continue the vector lines and find where they meet, okay, you can just continue these lines so you can see it, that would be theta right in there. Alright, so again, the idea is that theta is always the angle between the force and the direction of motion, in this case, x.
Can it ever be like negative? Or what can we
Yes.
Can the actual angle be negative?
Technically speaking, you could call certain angles negative and count for it, but we're going to look at the positive angles here. But theta could be negative. Yeah, it's just a revolution that's instead of going clockwise, counterclockwise. Instead of going counterclockwise, it's clockwise. And you're going to see later in math and in pre-calc for sure next year about angles that are measured with negative angles. And they'll call them coterminal and stuff. So I don't want you to think you can't be negative. But for the sake of this application of work, theta is the angle, or the absolute value, if you want to be more consistent than, of the angle. It's always the positive value there. All right, so that's theta. Now, another thing that was stated that Victoria alluded to, when is work negative? When is the work done negative? There was one instance we've covered so far. Yeah, when friction does the work. So if I pull on this object across the table over here, well, my force is this way, and the motion is this way also. So the amount of work I'm doing is positive. But if I'm pulling toward this wall, friction is pushing back that way. What's the angle between motion and friction usually? What's that full angle? 180, okay? So again, when an object is being pulled, let's say it's being pulled horizontally, so that means that the motion is also horizontal. Well, the angle between those is 0. There is no angle. They're parallel to each other. They don't look like they're, but if you move them up or down, they literally lie on top of each other. See that? The blue dashed line would actually lie on top of the black line if you put them next to each other. It's just hard to see. But the angle between them is 0 degrees. They're parallel. When two lines are parallel, there is no angle made up between them. They don't ever intersect, really. Now, if I have friction, though, and I realize, well, friction acts to the left, and I draw friction like this, and maybe for the sake of this part, I might want to draw my x a little bit lower so it's more obvious. So let's say displacement is to the right. Oops. Okay, so my displacement is to the right because I'm pulling on the object to the right, but friction goes back. So that's the angle of 180 right there. That's 180 degrees. And that's the reason why work done on an object by friction is always going to be negative. Okay, it's always going to be negative again because of the simple fact that cosine of 180 is what? What's the cosine? What is it? Negative 1. The cosine of 180 is negative 1. The cosine of 180 is negative 1. All right? So we have three instances that we've analyzed. We've analyzed when a force is being pulled and it's perpendicular, not perpendicular, and it's parallel, such as here, to the direction of motion. Then we looked at one where the force is at an angle, and then we looked at when we're analyzing friction. So theta for this FP would be 0, theta for this FF would be 180, theta here would be whatever it is between 0 and 90. Let's hypothetically say it's 40 degrees. Okay, whatever is given. So depending on the value of theta, you have to analyze this. Now, we also looked at this. What if your motion is vertical? Okay, what if your motion is vertical? So let's say we've got an object being lifted up, and it follows on like a little pulley system. There's a little pulley right here, and a force is being applied on the rope. But the direction of motion is vertical. Well, now here is theta. Okay, so motion could be vertical, and if your force is still at an angle, you still have that theta value, but now it's not the theta that looks like it's between the horizontal axis, but the vertical axis. So remember, just look at the direction of motion. In this case, the direction of motion is vertical. The force applied is at an angle like this. So here is theta right here. Okay, this is the angle right here, theta. Because this is the force being pulled at an angle. You're sitting there lifting on this cord, and you're pulling the bucket up like a coal shaft or a well in your backyard or something like that. You're pulling on an object and it's moving at an angle. So this is the angle right here.
So like, why does it really matter though? Like, would they already do the theta, like in that kind of problem? Though, like when they were given to you.
So in this kind of a problem, you might be told that the angle theta is between, like say for example this, all right? Say you're told the angle between the pull and the horizontal is 70 degrees. Well, then what do you have to use for your theta?
70?
No.
90 minus.
Oh, 90 minus 70. Okay.
You see what I'm saying? Okay, so I want you to recognize that. A problem could give you the angle between the pull and the flat ground because maybe it's a well and the angle that was measured there was between, so this is ground level, let's say. Maybe the angle that was measured was between the pull you pull on, 70 is not a good estimate for that angle. Let's say 40. So you get the angle between the pole and the ground level. Well, that's not what you want to use because motion is vertical. So you have to use the angle up here. So this is where I specified what theta is. Whereas when we did projectile motion, when we did vertical and horizontal, we looked at sine and cosine. In this equation, we're just going to continue to look at cosine. Okay, we could have stayed with sine and cosine and done that. But then we'd have to break it into Wx and Wy, and felt like that was a little more confusing than just leaving it with cosine always, and just knowing that theta is the angle between the force applied and the direction of motion. Now, the only time that you don't have work being done on an object is when they're perpendicular to each other. When they're perpendicular. When the direction of motion and the force applied are perpendicular. Why is that? Why is that? Anybody know? Jen?
Because cosine 90 is 0.
Yeah. Cosine of 90 happens to be 0. So if you recognize that cosine of 0, that was 1. Cosine of 180 was negative 1. Well, cosine of 90 happens to be 0. So if the angle you get in a problem is 90 degrees, or if they're perpendicular somehow, it means you're not doing any work to that object. Okay? You're not doing any work to that object. All right. Let's go to understand how this can be related to power. Okay, so we're going to jump to 5.4 and then we'll come back to 5.2, 5.3. So we've done all this stuff with work, right? So let's say part A said find the work done by a generator that's moving a turbine. Okay, or it's turning a turbine. So let's say you get an amount of work of 2,100 kilojoules as your answer. So it'd be 2,100,000 joules, really, but I'm going to say 2,100 kilojoules. So hypothetically, that's my answer. And then part B says the following. Find the power that the turbine generated if it took 3 minutes to perform the task. Part B says, find the power it generated if it took 3 minutes to perform the task. Very good. If you've got work, and you can see these as like step problems I give you for the math part. For those that have struggled with the math part at the end, okay, that's what I'm trying to get through here, so you can see steps. So in the second part, you're trying to find the power. And if you want to find the power, we're really looking at the work done over the time period. And if I told you it was 3 minutes, what would you use for time? What would it be? Yeah, 180 seconds. That would give you the amount of watts that were generated by the actual turbine itself, a power rating. When you get appliances, when you look at cars, when you get electric bills, they're always given power ratings. You're giving something with watts usually, okay, with watts. So that's what you're looking at here. You can get the power rating of the turbine or whatever the object was. Okay, I don't really care what the answer is, so don't go crazy. But I want to get the idea, okay? The idea again is that power is equal to the amount of work done over a time period, or the change in energy over a time period. Well, the amount of work done is really the change in energy. They're the same thing, okay? But depending on the problem, you might have to use one or the other.
So you really feel those should you always convert it before you start the problem?
Sure, yeah. When you have something with units that have prefixes on them, you should definitely change them back to the base unit before you do any calculations. Okay? Only one that's the exception is kilograms, right? Mass is always given in kilograms, which throws people for a loop. And the formulas are made for mass in kilograms. Again, one of those stupid adaptations that has been, kept over a long time. So yeah, kilojoules I would change. Let's see, what else can I do with this problem? Oh, what if I gave you a conversion and I said, figure out what this is in horsepower. All right, and I told you the following. Ooh, there's a lot more different things now. Anybody ever seen this one, by the way? That's to actually make a sound. It's supposed to be like a lightsaber. It's a terrible sound. It's like, like a real lightsaber.
Wait, how is it supposed to go?
Yes, exactly. I'll go to blue. Let's try blue for today. So, if you were given a problem, or if you're given the next follow-up that said find out how much horsepower that is, or what that's equivalent to, you'd have to be given the conversion. And 1 horsepower equals, I think it was 745.7. Is that right? Somebody converted it the other day. Watts. Okay? So, given that conversion factor, could you convert into horsepower? So you have an idea of numerically what it is. Well, this is just going back to really chapter 1. Okay, dimensional analysis, just convert. So you get an answer here. Let's see, these zeros cancel. So we're going to get 210,000 over 18. Anybody want to give me that number even though I said ignore it a minute ago? So what do you get with the amount of watts?
11666.66.
All right. So what do you get if you convert that to horsepower? How would you convert this to horsepower? You're in watts right now. You want to get back to horsepower, Marianne? Yeah, just divide by that quantity. And you can see that by doing this. In case you forget how to do this, please go back to dimensional analysis. Multiply this by the conversion factor. What do you want to get to? You want to get to horsepower, so put it up top. You want to get rid of watts, put it down below. 1 horsepower in 745.7 watts. So in essence, since this is really over 1, you're just dividing. Okay, you're doing 11,666 times 1 over 1 times 745.7. What do you get in horsepower?
Wait, then you just divide them, right?
Yep,
Yeah.
15.6. All right. Now, I'm not going to go into crazy detail, but horsepower has to do with the amount of power that an engine can generate, but it depends on the context of the problem. So I gave you an example in class, and we did, I think, where like a car accelerated from like 7 miles an hour to 22 miles an hour. It was very little horsepower. Again, because that does not tell you that the car can only generate that much horsepower, but in that instant, for that task, that's how much horsepower, how much power that engine was generating. But that amount of energy, or that amount of power itself can fluctuate. What was the other formula for power that we should know? There's one other one. Yeah, F times V. So power equals F times V. All right, please make sure you use this when you have a force and a velocity. Don't go into crazy depth and try to rederive the other formulas if you're given something like distance and force. Okay, if you're given distance and maybe you're given a time period also, all right, you might be tempted to go ahead and change that. But if you're given force, distance, and time, all right, if you're given force, distance, and time, well, then you would probably just use work over time, because work is force times distance over time. So you can go right to that. Or technically, you could do distance over time to give you what the speed is, and then take the force. But it's the same answer. Okay, just pick one or the other.
Doesn't it have to be like constant or something? Or
That's
what
correct.
does that really mean though?
So for example, if an object's velocity is changing from 3 meters per second to 20 meters per second, you would probably use another form. You would use your delta E over T, because V would be changing. This is assuming V is a certain specific number the whole time. This is like your average velocity, actually. Okay, but I don't really talk much about average velocity form in the beginning of the year, and I remember not doing it with projectiles, so I'm not going to make you go through that, but it's simple just to do it with delta KE instead. All right, so remember this other formula. Here's the third one. You can just think of change in energy over time. So if an object accelerates and changes its velocity, well, a change in velocity means a change in kinetic energy, so this delta E would really become the change in kinetic energy, KEF minus KEI, all over time. Again, in a problem where you have multiple velocities, you have a starting velocity and an ending velocity, and you're trying to calculate the power delivered to increase the velocity of the projectile or object. All right? How about 5.2 and 5.3? I think this is the tougher stuff. And 5.3, you're going to notice, I hope after today, that is actually pretty easy as well. Okay, you're just applying formulas. But 5.2, we need to remember all those formulas. They're on your sheet, but you need to remember what they're all for. So what do we have from 5.2? Give me something about 5.2. Give me one thing.
Okay, potential energy equals mass times gravity times height.
Good. That's one. Gravitational potential energy is mgy. What else? Somebody else. Ed? Okay. And finally, the last part?
Potential energy of the spring equals 1/2 kx squared.
All right, now let's comment on all of these. Very good. Good memory. Okay, but these are given to you on your formula sheet. Let's comment about each of these. What can you comment about with potential energy? What's something you know about potential energy? The first one, gravitation. Jake?
It's not moving energy, it's like stationary.
Sure. So this has to do with when an object is at a given height. Oops, let's spell backwards. And not given a velocity. Okay? Not given a velocity. What else?
We have potential energy at the highest point, something.
So, all right, at the highest point you have PE max. And then, what do you usually do in a problem to make it easier on you? What's an easy technique to make the problem so that you don't need potential energy in the other part? Remember this like kind of trick?
Just need zero.
Yeah, what do you do to get it to be zero? What do you have to call that? Yeah, call ground level either the beginning or the end of the problem. So let's say we have a problem like this, okay? An object falls off of a cliff and on its way down, so make believe this is the ocean. On its way down, we want to find out the speed at this exact point in time. Call this ground level so that there's no PEF. Is that clear? Think about it for a second. At the top here, it's got potential energy. It falls off, so there's no kinetic, let's say. It wasn't pushed off. It just falls, dropped. Okay, dropped from rest. So there's PE at the top. if you call this ground level there, then at the bottom there's only kinetic energy. Technically, we could say there's no height if we call that ground level. So that means that ground level is a reference point. It's a reference line. When you worked on that simulation lab, remember you had to move the PE reference line to become equal to the bottom of the skate ramp? That was so that you had no potential energy at the bottom there, so that it was considered like it was at the bottom of the ground or it could not fall any further. So it is very useful to set the reference line value equal to one of the heights in the problem, whether it be the beginning or the end of the problem is up to you. Okay? What else about potential energy? It's a function of height. It's also a function of the mass. And it's a function of the planet that you're on. Okay? Because G changes based on the planet. Specifically, though, in this chapter, we've seen it as really a function of position or height. Okay? Position or height. What about the other type of potential energy in the spring? What do you know about the potential energy in a spring? What is it a function of? How far you do what? How far you fill in the blank? How far you not move? I mean, you could use the word move, but there's a better answer. How far you compress the spring or stretch the spring? And that is represented by what variable? X. Okay, be careful here, please. Jot that down if you forgot that. X in this formula at the bottom here, this X right here, has to do with the compression distance or the stretched distance. It's not displacement. Please keep that in mind. So if I tell you that a spring is normally 4 centimeters long and you want to launch something off of it, so you compress it and you lock the spring mechanism. Okay? And you want to figure out, it's normally 4 centimeters long, you compress it so that now it's only 1 centimeter long. What is X? Is it 4? Is it 1? Is it something else? 3. Okay, so it started to be 4 centimeters. You compress the spring till it's 1 centimeter. What's the change? Okay, the change is 3 centimeters. So this X here is really like a delta X. The reason I honestly don't put delta X there, because then people start thinking about position and like final minus initial with position, which is similar, but I'd rather you just remember that it's the compression distance. Okay, the compression distance. What else? What is K? What is K? And give me some examples also. The spring constant. Very good. The spring constant. What could you tell me about K? Can you give me some sort of a relationship that exists? As K does this, what happens? Or as K does this, what happens? So like a higher K means what kind of thing?
Well, it's like as K goes up and B goes down.
No, they're directly related. It's the numerator, right? Only when it's in the denominator are they indirectly related. So it's directly related. You could say as K goes up, the potential energy stored in the spring would go up. So a stronger spring takes more energy to compress it, and therefore you're storing more energy. Think about it. Take a really strong spring. It takes a lot of force to compress it versus like a spring in your pen. It takes very little force. Because it's taking you more energy to compress it, it's actually storing more energy. And that's because these are directly related. But what about K, and if K goes up, what do you know about the spring itself? What could you say, what relationship exists there about the spring itself as K changes? Sure, that's a good word. As K goes up, it's a stronger or more rigid spring. Okay, again, higher K values are more rigid springs. For example, the springs, and I used this example last time. Here's a different example. You know at the end of the railroad, Long Island Railroad or Metro North, have you ever gone to the end of the line? One of the ends, there's always some sort of a cushioning. You don't always see it. But if you look down the tunnel, and I've seen it in Boston at the Amtrak station. There's an Amtrak line that terminates in Boston, and it doesn't go any further. And when you arrive there, you actually pull into the station, and you see these spring beds, like in a mattress, the springs that are in old mattresses, but huge ones with diameters of springs like this big, and they're helical, and they're conical, so they come to a point like this. And that's because what would happen if the brakes stopped to work, right? Instead of the train running into the station, what happens? Yeah, it hits the spring, which absorbs the energy. What kind of energy does the train have when it's moving? And then it stores it into spring energy, and then the spring pushes back, pushing it back the other way. Now, if there was too much kinetic energy, and you did the problem and you said, all right, KE equals 1/2 kx squared, and you tried to solve for x, and the value of compression was more than the spring's length, it means it would go through the wall. So say the spring length was like 10 meters, which is reasonable for these, or let's say 3 meters, okay? So the spring length is about 3 meters long. If you get an x value of 1 meter, it means that the spring compresses this far and then pushes back against the train. But if you get an x value of like 5 meters, that means that it would compress beyond the wall, right? So what would happen is the spring would not be strong enough. You would need a higher K value. A higher K value so that the X value goes down. Let's do a problem of that mathematically. Okay, let's do a problem of that. We'll go back to KE in a second. So let's say the train is traveling with a velocity of 20 meters per second, and the mass of the train is 20,000 kilograms. And you know that the spring, let's say the spring's K value is 4,000 newtons of force for every meter. I'm completely making these numbers up, so let's hope it comes out to be somewhat reasonable. And the question becomes, how far will the spring compress? Is this a feasible arrangement or setup? Okay, how far will it stretch or compress? So for a problem like this, if we look at our givens, we think about back to the problem that when the train is moving, it's got kinetic energy. It's moving that way. It hits this coiled up spring that's adjacent to a wall, and when it hits the spring, it stores the energy in the spring like that. Eventually, when the spring stops compressing, what has to happen for that train car? In an instant in time, it has to stop. And then maybe it gets shot back off, right? So it compresses the spring, and then the spring would push back. But for an instant in time, it does this. Right, here's the train. The train's traveling, hits the spring. It pushes the spring, it stops, and then the spring pushes it back. So it does pause for a moment in time. And if you consider that moment in time, you know that there's no KE. So this is a complete energy balance. So for a problem like this, we look at section 5.3, and we say to ourselves, well, the mechanical energy involved is always conserved, and therefore, we know that the KE before equals the potential energy in the spring after. That comes from this formula, MEI equals MEF. Remember that energy is always changed, but never lost nor gained. You can't just lose energy. Even if energy goes to friction, it's technically not lost. It's just converted into frictional energy or thermal energy. So for a problem like this, we start by saying, all right, well, 1/2 mv squared equals 1/2 kx squared. What should I do to make this problem easier on me? Cancel the 1/2s, right, on both sides? 1/2 is on both sides. M is not on both sides. Okay, we can't drop off M like we did in other problems. We're trying to figure out what x is, right? The compression distance. So mv squared over k, all under a radical, is what x is equal to. So again, divide by k, and then take the square root to get rid of the square next to the x. Divide by k, then take the square root. What do you get as a result? Can somebody check out a number for this, please? So we're going to have 20,000 times 20 squared, all over 4,000, all underneath the square root.
So the 1/2 cancels.
Yeah, because they're factors on both sides of the equation. Remember, if we had m in every term, we could drop them off. We have 1/2 in every term, so we can drop them off. 20,000 times 20 squared over 4,000, all underneath a square root. What do you get, Kev? 44.7? 44.7 meters. So, that doesn't seem like it's a good answer. Do we want a spring that stretches 44 44 meters, that's like half a football field. The spring would be ridiculous in length. So if we don't want that length to be that way, what should we do to the spring? Make it, what? What's the word you're using?
Like harder, stronger?
Yeah, stronger. You said rigider, you were saying? Yeah, more rigid. I don't know if that's a word. That's why I didn't know what you were saying. Stronger. Make the spring a higher K value. So when engineers design stuff, they look at parameters and they parameterize. So they look and they say, well, if I want the displacement X, take a look at your solution. This is where you really get physics now. Look at the solution. The solution for X is indirectly related to K. See how these are inversely related? As K goes up, X is going to go down. So as Jen said, make K more, or make it stronger, and the X value will go down. So let's try K. Instead of 4,000, maybe let's try 35,000. So use the same exact work, and now plug in 35,000 for K, and see what you get for X. Now, you would never just do this trial and error. You would say, I need X to be like 2 meters, set X equal to 2 meters, and then solve for K. You know what I'm saying? You list what you want for X, really. But just to give you an idea as to varying these parameters to see the effect on the problem. What do you get if you let K be 35,000? So when K was 4,000, we got 44.7 meters. Okay, but if K is 35,000, a much stronger spring, what do we get for X instead? 15.1 meters. So again, still probably too long for a design at a train station, but the idea that as K goes up, it's a stronger spring, so it's not going to compress as much. It's more rigid. It's like springs in your cars. If those springs weren't strong enough, your car would do this on every single bump. Okay, that wouldn't be very comfortable. You want the spring to be what's called perfectly damped. A system is perfectly damped when there's a spring and what's called a damper. A damper, just so you know, this is a side note, but it's good to know. When this door closes, right there, see that? That little pause? It's a dampening effect in the hinge. It used to be that doors were made with these little cylindrical chambers, and you would see this little cylinder that looked like a piston on the top that was connected. And what would happen is the door, inside that piston, there would be a little disc, and there'd be a fluid in there. And the disc would move as the door closed. And when it caught the fluid, it would slow it down. Like, have you ever taken your hand underwater and done this underwater? You feel like a viscous force, it's called? That's what the old door setups used to be. Now they're different. Now, believe it or not, if I can see it on here, it's right here. The damper is actually contained in here, and it's a mechanical damper that uses torsion. You alter this, you change the tension in the actual screw. So if you make it tighter or looser, it overdamps or underdamps the door. Okay, but the idea behind it is that it's perfectly damped. Well, springs are used in these systems, so you want to analyze the springs to see what you can do with them. Now, the third type of energy that we alluded to just now, but we didn't discuss yet, was kinetic energy. And kinetic energy is a function of what? Good. Okay, kinetic energy, as we know, is 1/2 mv squared. And there was something also, a theorem that we learned with kinetic energy. What was that theorem?
Kinetic energy.
Kinetic energy and?
I forgot. I'm mixing up.
I thought you said it, that's why.
Root?
Not root, it wasn't root, I thought you said something else. The work kinetic energy theorem. Okay, the work kinetic energy theorem, which states what? Which states what, Marianne?
The work net force equals delta K.
Yeah, the work done on an object that's moving horizontally, that doesn't change its position, is equivalent to the change in kinetic energy. Why am I not saying vertically? Why am I saying horizontally here? When you change something vertically, what other type of energy do you change? Potential. Okay? So if an object changes vertical height and it changes velocity, you should use your conservation of mechanical energy. MEI equals MEF. But when they tell you the work done on an object, and you know it only changes its velocity, use the work kinetic energy theorem. Alright? This is really stated as follows. Bless you. All right, that's really what it's saying. Final minus initial is equal to the work done. Now, the formula for work done is usually FD cosine theta, so at least you know what that would be. And kinetic energy, we know. So in essence, although you're only given this formula up here, right? This is the formula you're given in your formula sheet. W equals delta KE. It's really this. Okay, this is really the formula. Remember the question you did with the socks and the people who recorded their videos? That's what this was from. What was the work done by in that problem? The force of? Friction. Yeah, good. Friction. It was causing you to slow down as you slid across the floor. All right? The work done by friction. So, let's think about this for part twos. Because I know I do a lot of conceptual discussion, but we don't always get into a lot of part twos here. Part twos, here's what you can expect. Expect a problem where you find the work done. Right? Then, either from that, maybe you find the power, because it's work over time. Or if you find the work done, maybe you find the change in velocity, because of the work kinetic energy theorem. So those are the part A, B type problems you could expect. That's what you have to think about as you're doing this when you're practicing. Okay, you found the work done. Well, you now found the work done, so find the change in velocity. Maybe the object started from rest. And if it started from rest, now you just cross this off. And all you have to do is solve for VF. Yeah?
Where does the force of friction is supposed to 180?
Yes. So that's why if friction is doing work, it's causing it to come to rest at the end, right? Well, if an object comes to rest at the end, then VF becomes 0, right? So as a result, here's what happens. If there was friction doing work, you would solve for the initial velocity it started with, or maybe you were given that, and you're trying to find distance or something, whatever it is. But VF is 0, so this drops off. So you end up with a negative sign over here, but the cosine of 180 is also negative 1. So this becomes negative 1. So the negative here and the negative here end up canceling, which allows you to get a positive distance traveled. Okay, we did that example with the sock problem, okay, where the negative dropped off. Let's do an example with conservation of energy. All right, conservation of energy. How are we doing on time? 6 minutes? Thank you. So, let's say an object is fired from the ground from a loaded spring or a Nerf gun. You take a Nerf gun, right? Let's say we'll call this ground level. You shoot a Nerf gun off at an angle. So there's some sort of a spring I'm going to draw like that because it's at an angle. Here's the object. It's launched and it starts flying. At a height of 20 meters, okay? At a height of 20 meters above the ground, determine its velocity if the mass of the object is 50 grams, if the spring's constant is 40 newtons per meter, and the compression of the spring was 4 centimeters. Find the object's velocity when it's 20 meters above ground level, when it's up here. So I start with conservation. I always start with conservation with these problems. And I say to myself, well, the energy before equals the energy after. Well, here's before, right here. Here's after, up here. Remember, you need to truncate the problem. If this object had continued down to the ground, well, when it hits the ground level, it no longer has potential energy at all. It's only kinetic there. So then we would have only kinetic at the end. But at the top of the path, what kind of energy does it have right now? At the top of the path, what kind of energy does it have? Potential and kinetic. Although it technically pauses vertically, it's always moving horizontally. Remember that theorem from projectile motion. So at the end of the problem, we've got potential energy due to its height, kinetic energy due to its motion, and what kind of energy is it in the beginning?
Potential.
What kind?
Spring.
Spring potential only. Very good. It's not moving, please. So many people keep putting KE with the spring. If a spring is loaded and there's energy in it, and it's waiting to launch, and there's energy in the spring, it can't be moving. I mentioned this in the class yesterday. You're never going to have KE and PES on the same side of the equation. It just doesn't work. If it's moving, the spring itself, think about it. If an object hits a spring and it compresses it all the way, and it's fully compressed, it's got to stop. So there's no kinetic energy when it stops, and that's when all the spring is loaded with energy. Or if you're launching something, you compress the spring all the way down, and then you pull on a pin, and it releases the spring and launches it. The instant before you pull on the pin, all the energy in the spring, right? It's not moving. So you can't ever have kinetic energy on the same side of the equation as potential in the spring. Now we just go ahead and plug in our formulas and solve. Again, this is not difficult. The difficult part is not the mathematical. It's the actual writing of the equations here. So that's what the difficult part was right there. After this, I mean, this is easy now. Literally, write your equations. Now, I can use YF and VF, but because there's no YI and VI, I'm not going to specify for final. Okay, again, based on the context of the problem. Your goal was to find the velocity. You've got everything else. Subtract mgy. And then divide by 1/2 m. Yes. You can't because it has to be in all the terms. Remember, which term is it not in? And that's why you can't cancel masses also, Jake. Look, mass is here and here, but mass is not in the spring. Okay? And then I take the square root to make it v. Gets rid of that square. So that would be your generic solution for the velocity of the object at the top of the path. At the top of the path. Now, follow-up question. That's part A. Real quick. Part B. What about the velocity when it hits the ground at the end? All you do is this. Ready? Cross off mgy. Because now if it hits the ground, as it goes up, right, it has potential up here. But when it comes back down to the ground, all the energy is kinetic. There's no potential energy due to height. So just drop this off, and now you can get the velocity when it hits the ground. Isn't that cool to see that? How you can change your generic solution? Just drop that off, and now the answer is referring to the velocity at the end of the problem. I'm going to put up a review sheet on documents and handouts. It's just like a little diagram that Jen had from one of her other class that she had seen. Okay, and I adapted it for our class. Okay, so you can thank her for bringing that up, but it kind of flows through a flow chart of ways to look at problems. It's very simple, but it might help. Okay?